Attendees are in listen-only mode.
Good morning, everybody. I'm Woody Cash. I'm the SCTE Content Knowledge Officer for the Golden Gate chapter. And today we're going to talk about SCQuam OFDM OFDMA and DOCSIS functions. Our presenter will be Juan Castro. Juan is the Solutions Engineer for Viavi. I've known Juan for many years, and he's a very good presenter. So hopefully we get a lot of folks on the webinar today, and I think you're going to learn a lot. But first, I want to talk a little bit about SCTE benefits. I'll just go into some personal experiences. SCTE. I got involved early on in my career, and one of the things that I developed over time was this vast network of people with, vast amounts of knowledge. So if there was ever a difficult question, I could almost always find somebody or knew somebody that had the answer. I didn't have an answer. I knew the answer to some things, maybe a lot of things, but there was a lot of things I didn't know too. But having that network was very important in my career, to be able to find somebody that could get the answer instead of having to go through a long process of elimination to find solutions to problems. I would also like to say that, we have a vast amount of training out there online, and for those that are CAP members or Cable Labs All-In members, take advantage of the trainings. Now that I'm no longer employed by someone who's a CAP member or a Cable Labs All-In member, I can see the prices, and I can tell you they're not cheap by any stretch. So take advantage of those. Take advantage of those courses that are available, especially the ones that are free to you. I guess that will conclude that. Just like a couple of housekeeping items, you all are muted, but you do have the availability to get into the chat or questions box and put in your questions. I will be pausing one occasionally and go through the questions so we can get those answered. I'm also going to be sending out a couple of questions for you to answer in a poll. And by the way, if you get it wrong, it's no problem. You won't be identified whether you get it right or wrong. So please take a second to reply to those so we can go over those at some point during the presentation. With that, I'm going to turn it over to Juan. Juan, welcome and thank you. Thank you for doing this presentation.
It's my pleasure, Woody, and thank you for your service to your local chapter for many, many years. And everyone else, welcome aboard. Again, my name is Juan Castro. Just a little bit of my background. I've been in the industry for 30 plus years. I'm currently going on my 5th year on the National Cable Games Committee, and also been a director for the Los Angeles chapter here for the last 30 years. And I've been working with Viavi for the last 20 plus years. Just a little bit of my background. So here's some of the objectives we're going to try to accomplish today. And really the goal is to show the difference between the earlier versions of DOCSIS, DOCSIS 1, DOCSIS 2, and DOCSIS 3.0, 3.1, etc. And really how the different types of carriers, whether it be single video, single DOCSIS, OFDM or OFDMA upstream, the different capabilities to sustain different types of issues that we have to deal with on both the upstream or the downstream. All right. So this is our objective for today. Again, if there's any questions on this session for the next hour and a half or so, please put them on the chat, and Woody is going to assist me while I'm keeping an eye on all this other stuff up here on the screen. He's going to help me out with any questions that might pop up, and I'll try to take care of them. Thank you, Dan. Okay, so let's go ahead and start with a general understanding of our industry, and where we are and where we're headed. Possibly systems are different. MSOs are headed a little bit different in certain areas. And again, the main most of you have probably seen this graph here at one point or another. If you've attended SET presentations for DOCSIS, you can see where we've gone from dial-up to DOCSIS 1, DOCSIS 2, DOCSIS 3, DOCSIS 3.1, and eventually where we want to be able to deliver with DOCSIS 4.0. Ultimately, you know, to deliver, you know, 10 gigabits per second on the downstream, and on the upstream, you know, symmetrical services. Those are definitely challenges that are coming out of our industry. I mean, you know, think about where we've been and where we are today. There's certainly been some challenges just to get to this point, but it looks like we have further to go with. All right. Again, this is just from a DOCSIS perspective, but the reality is you have other technologies that are competing to deliver broadband services, and one is RFOG, for example, using multiple lambdas. You know, this is an example of 20 kilometers, X amount of homes, for example, one lambda used for downstream, another lambda used for upstream for DOCSIS capability, right? So this is another way of delivering the services to subscribers, breaking up the upstream and the downstream capability. So, you know, ultimately, who's going to have a fatter pipe at the end of the session, right? Whether it be the optical, whether it be the RF, et cetera. So, I mean, this is just another technology that's been implemented for several years in order to, again, to continue to compete against RF technology cable systems. The other one is EPON and GPON. I mean, multiple lambdas on the downstream, you know, enable each individual lambda to segregate both for RF, for 10 gig, and GPON, for EPON, et cetera, and several lambdas for upstream, 1310, 1270. Again, they all vary, and you have to work with the manufacturer, obviously, that you're working with to understand the layout, but these are pretty common standards for EPON and GPON as an example. And again, another comparator when it comes to RF delivery, you know. And you can go forward without discussing DEA architecture or distribution access architecture versus the current architecture that we have right now. Most of our systems, not all, but most of our systems still deal with a centralized network. You have a centralized head end or hub where you have all the modulation, the CMTS, and we basically combine all of the optical, all of the carriers, put them on an optical analog link up to the optical node, and then convert that back to RF for the delivery to our subscribers. So this is changing. It's changing rapidly as well. I mean, and this is another way of competing against fiber. You know, no one can just change the entire network to fiber immediately. So how do you continue to evolve the fiber network and still utilize all of the passives and upgrade obviously some of the actives to continue to use the RF link to the subscriber. So we're moving from a centralized network to a remote PHY network capability, and therefore moving some of these features from the central head end out to the optical node. Right? So we're going from an analog link to a digital link, delivering a 10 gig digital link, and then modulating and demodulating the downstream carriers at the optical node, at the remote PHY node, in order to produce better MBR, better services to the subscribers. All right, so this is another method that has gone forward. So think about your system that systems who upgraded, you know, and then all of a sudden, you know, the pandemic hit, systems who, you know, upgraded to 85 megahertz, for example. You know, most systems are 5 to 42, and then when they applied remote PHY, some systems went to 5 to 85 megahertz. You know, and you know, all of a sudden now systems are looking at 204, right? So now they have to come back and upgrade this portion of the system back to 204 as well. So the next step in the evolution of this, some systems are just going to skip remote PHY, and they're going to go ahead and move the MAC layer out to the optical node. And again, the ability to do and modulate, demodulate everything at the optical node. But in this case now, remote PHY was going to support 1.2 gig on the downstream, for example, and remote MAC PHY was going to support 1.8 gig. But I think over time, MAC PHY will be, remote PHY is also going to be able to do that as well. So it's kind of a mix between the two, but ultimately the ability to move the MAC layer into the optical node at that point. And then we're going to go ahead and move completely more features out to remote CCAP at that point. So this is the architecture that we're moving forward to, all right, in the future. Again, as we continue to deliver fiber deeper and deeper, but again, is it easier just to, continue to change and upgrade the active devices and still utilize the RF portion of the network, right? So this is where all of the systems are kind of going forward with, right? So whether the expansion of bandwidth is to 1.2 gig or 1.7 gig or 1.8 gig, I should say, or eventually in the future to 1.8 gig, these architecture, capabilities will be able to support that as well based on the manufacturer. All right. So again, those is just examples of where we're going from that perspective, right? Let's look at bandwidth expansions. So here's an example of a subsplit. Right? Most systems are generally 5 to 42, and over time, they've added an OFDM carrier. Most systems carry at least 4 single QAM carriers, but in some situations, they've added an OFDM carrier down at the lower end between 6 megahertz and 20 megahertz, for example, and eventually, over time, started to remove the other carriers, right? So as they progress with more subscribers having DOCSIS 3.1 modems, they started to move the OFDM carrier, making it much more wider to support, higher throughputs, and therefore removing single QAM carriers from that perspective. So from a downstream perspective, most systems are still delivering 32 single QAM carriers for DOCSIS, and generally, a 96 megahertz carrier per se, right? Some systems deployed went from a 96, have 32, and deployed a 92 meg. So a service group can be considered 32 single QAM carriers in one OFDM carrier, which could be 96 or it could be 192 megahertz wide, for example. Right? So while systems are trying to deal with, it's not easy to expand the upstream bandwidth without actually, changing the active devices themselves. So basically, they continue to grow the OFDM carrier as we move forward, more and more subscribers having 3.1 cable, modems that are capable of sustaining the upstream capability for OFDM deployment. So again, this is one way of doing that. So again, a lot of systems moved forward before the pandemic to deploy 5 to 85, right? So in a 5 to 85 megahertz network, you can have a combination of single QAM carriers, for example, all the way up to 85 megahertz. But in this situation, they mix a combination of either 1 or 2 OFDM carriers and single QAM carriers in order to meet the requirements of 3.0 modems and 3.1 modems themselves. So the variations are different, all right, but the expansion of bandwidth is still the same thing for the downstream, maybe 108 megahertz to 1 gig. You still got obviously your digital video carriers and also your DOCSIS 31 and 1 OFDM carrier, for example. So they vary. So this is the next kind of generation of where systems are looking to move forward, right? So again, moving out to 1.2 gig is actually correct, should be 1.2 gig, and deploying their second OFDM carrier. Some systems are 1 gig, have deployed their second OFDM carrier, and therefore they have the ability to bond higher. So a service group can be 2 OFDM downstream carriers and 31 single DOCSIS carriers, for example, right? So this is one service group. I do have some customers who have completely removed all of their digital video carriers now and are completely all DOCSIS and have deployed their second service group as well. And that's why your meters today have multiple MAC addresses. They need to be provisioned in order to, to do DOCSIS testing. So you'll be able to do service group 1, service group 2, et cetera, right? As more and more of this is starting to happen, obviously with the expansion of the bandwidth and supporting single QAM carriers all the way up to 85 megahertz, and from that point it will be OFDMA carriers all the way up to 204 megahertz. So this is the high split, and it could be a combination of variations. Well, I mean, as we look at these scenarios and the deployment of these single QAM carriers and OFDM carriers, right? The next evolution has already been spoken for several years, and the next one is really, you know, OFDM or 4.0, for example, and the ability to deploy FDX, full duplex, right? So they want to be able to expand instead of 204, go all the way to eventually 300, 400, 500, and 680 megahertz on the upstream. So you will still have the legacy upstream capability, for example, and the downstream will now be converted into upstream. So you'll have a combination of downstream and upstream capability carriers that will be able to support the ability to do bidirectional testing. So this is kind of unique because, I mean, this is a big change from going from a fixed upstream bandwidth to a bandwidth that will be, you know, bidirectional and will be utilized from both, you know, both upstream and downstream capabilities from these devices. So that means that the CMTS will have to control traffic based on the requirements on the downstream, based on the requirements that the customers require on the upstream, as we start to segregate the downstream portion of this in order to start to deliver these types of services, right? So if 10 gig symmetrical service is the requirement, think about this concept, right? So again, extending the bandwidth to 680 megahertz, and then deploying the rest of the single QAM carriers above, all the way up to 804 megahertz. So one of the things that is being looked at is dealing with echo, right? And this technology can only handle at this point, based on what based on my knowledge on this, is that and it was deployed several. It wasn't deployed several years, but it's been around for several years. It's just it was more cumbersome to deploy, and I think the technology's finally moved forward with the active devices to support this. So the question is, how many amplifiers can you have in cascade in order to support this type of technology, right? So you know, based on the last expo, and even from previous, you know, so your active number of amplifiers are only at this point, I believe, is only 3 active devices that can support full duplex. That means that if you have an optical node with a line extender or multiple line extenders, for example, they have to be able to switch on the fly, you know, in order to deal with upstream and downstream capabilities. So for those of you who had, some of you might have gone to Expo and you would see some of those scenarios that were played out there in demonstrations. It's pretty amazing to see that happening. But one of the issues that starts to deal with when you don't have a segregated upstream and downstream, and you're bonding upstream and downstream within the same bandwidth, one of the things is echoes, right? So how do you deal with echo canceling, right, between modems that are transmitting upstream and downstream capability at same similar frequencies? For example, instead of just transmitting on the upstream 5 to 42 or 85 to 204, for example, now they're using the downstream and upstream for upstream capabilities and therefore producing echoes. So therefore now the set-top box will have echo canceling. The active devices will have echo canceling as part of their repertoire to manage a full duplex type of network. All right. Again, there's a lot more information and cable labs that I'm going to be able to cover here, but it is pretty amazing to see that going forward, right?
Hey, Juan,
so let's go ahead. Yes, go ahead.
A second. I have a question, and I wanted to kind of go over the first poll question, if I may. So the first question was, what does the acronym OFDM stand for? And we got 64% participated. 84% actually got it right. And I was just doing a little studying with orthogonal last night, and an interesting thing. It's a math term, and it's and it's when its parts. If you sum its parts, it comes back to a zero value. And it maybe at the later on when we get to that part, we talk about getting those carriers at a tight spot. We can kind of cover that. But I also had
Sure.
a question about could we maybe go back to the distributed access architecture slide?
Yeah.
Talk about remote cap and our CCAP, and what are the benefits to moving to the logical link security or link control and link security components to the node housing? Is it the cost primarily reason why we don't do it today? So thank you for those questions, Don.
I'm sorry, this is the slide you were looking for. Is that what you're talking about?
Yes, I believe so.
Yes. Okay. I'm sorry, I was trying to find this here. I'm sorry, what was the question again?
A question is, what are the benefits to moving the logical link control and link security components to the node housing? And is it the cost of the primary reason why we don't do it today?
You know what? That's a question that's a little bit higher for me to answer, but ultimately, I'm just thinking about it from a perspective of managing us. Most MSOs have a central center nowadays, right? And you have hundreds or thousands of headends and hubs. Think about the ability to move all of this infrastructure to the optical node, the MAC layer, all the physical layer, right? And therefore the master head-ends hub sites at that point become literally just optical switches. So from that perspective, ultimately down the line, I mean, there's got to be a great benefit of moving all of that to the field. Managing it is another issue, you know.
So the challenge seems to be more logistics than it is actual cost, because the cost benefits there. But the
long term, absolutely
difficult.
Absolutely, yes, and I think why did systems decide to go to a remote PHY? Some systems are waiting for a remote MAC PHY, for example, right? And some systems are going to wait for CCAP capability. There's definitely several priorities that they're looking for, and positives of moving to MAC PHY and just waiting for. Initially, when remote PHY was going to be able only to support 1.2 gig, remote MAC PHY, my understanding was that it was going to support 1.8 gig. So why come back and do this again later? Why not just wait for remote MAC PHY? But I think what happened is the difference between the two technologies, remote MAC PHY will support 1.8 as what I've heard when I was at Expo by the manufacturers as well. It's a mixed mode between the two now. So from a bandwidth perspective and just delivering in what's been going on with over-the-top delivery of, our customers are using their Wi-Fi, for example, TV, and looking at internet delivery services which includes video, to their television sets, right? So that is reason why a lot of these systems are removing their digital video carriers and are completely going all DOCSIS. That is a completely different change from what we've done for years. So analog carriers to digital video carriers to possibly all DOCSIS capability. And this infrastructure will support all of that as well. I mean, obviously it will support both, but in all DOCSIS capability of basically moving the MAC layer and all the infrastructure out to the optical node, that will definitely, I will see that, I would think that there's a lot of benefits there for an all DOCSIS network at a future date. That was my best answer, Woody.
And it was a good one. Thank you, Juan.
Okay. All right. So let me back up a little bit and look at DOCSIS, right? So let's look at the where we are right now. Most systems have got 31 single QAM carriers and one OFDM carrier. For those of you who've been around the block, you remember a lot of these acronyms: DOCSIS history, DOCSIS quantum. This is kind of what I'm going to cover just briefly in this next module, right? Which includes OFDM later on it. But when we look at a screen and we see the number of carriers in an OFDM carrier, right? Certainly have a lot more information than when we deal with the single carrier itself. For those of you who've been around the block, remember when we did a single channel DOCSIS carrier, that was like a big deal. Single carrier upstream, and look at the type of modulation that we did. And then it eventually went from single to 4 carriers on the upstream to 8 carriers bonding to multiple carriers. Now systems are moving to 31 carriers and having 2 OFDMA carriers to deliver, well over 2 gigabits per second on the downstream. And not only that, but back then when we were bonding the carriers were pretty close together. Here we're only bonding one. We weren't bonding basically one upstream, one downstream carrier, but now we're bonding all of these carriers to deliver data at one possible time. So therefore, linear distortions that are very, when you spread the carriers so far apart, you can have other problems that can help you or affect you, I should say, both upstream or downstream. So the more you expand the bandwidth upstream or downstream, and you end up with roll-off suckouts and whatever other problems you have, these are the issues that can impact these types of frequencies as well. So I mean, OFDM, ortho frequency division multiplexing, the physical link channel, the next cohort pointer, the low density parity check, which is a technology to help for burst protection on the downstream capability and upstream capability, single carrier QAM, single carriers. We're going to talk a little bit about that. So let's talk a little bit where we've gone to. I mean, obviously, an OFDM carrier can be deployed at 24 megahertz. More systems deployed a 96 megahertz carrier can go 100 and 192 megahertz wide, for example. Flex modulation. I'm just going to tackle a couple of these things just to continue to move forward. They really utilize the spectrum much more efficient than we've done with a single QAM carrier itself. So levels of modulation based on the MER. So I mean, based on the communications between the CMTS and the set-top box for OFDM and profiles, the ability to change MER requirements and profiles, that's a big deal. I mean, instead of sticking to one type of modulation, which we're going to talk about. So let's talk about where we were in the past. Obviously, we're already in the future. So back in 97 to 99, a single carrier, one single QAM carrier on the downstream, and the type of modulation that we've chosen over the years. Why did we choose QPSK? I mean, it was very robust. I mean, the systems, think about back then, the systems had long cascades, 12 amplifiers, 20 amplifiers, 30 amplifiers. So if you're going to deploy a digital carrier, where's the digital carrier on the downstream and what type of modulation you're going to deploy in order to deal with long cascades and all this excessive noise. Other than the set-tops buying pay-per-view on the return, there wasn't a lot other traffic other than maybe some video. Some systems use the upstream for video services, for analog, deploy, sending a video carrier upstream to another location and up converting those type of things. But primarily this was the DOCSIS capability of that, right? And then over time, the carrier became wider. So they went from a much wider carrier that they needed to deploy from a DOCSIS 4.1. So DOCSIS 2.0 came about, the ability to do a 64 QAM in a 256 QAM carrier. That was a big deal, right? I mean, higher throughput on the downstream, higher throughput on the upstream, but it's still only one carrier. And that carrier generally was in the middle of the bandwidth again, just like the other carrier, to make sure it was not impacted by roll-offs, suckouts, or excessive noise that are generally from 5 to 15 or 17 or 20 megahertz. So it's just at the very top where the noise would generally start to concede at that point and not being impacted by that, especially with 64 QAM. And then DOCSIS 3.0, came around in 2006, where we started to bond more channels. So and this is really what's changing, what not only changed technology, but it also had to change all our tools. All our tools had to continue to change in order to verify all of these different services, right? So bonding on the downstream, bonding on the upstream capability. Again, it's just a high level view of where we've gone from DOCSIS 1, DOCSIS 2, and DOCSIS 3.0 to where we are now with DOCSIS 3.1, which is, interesting because DOCSIS 3.1 is still backwards compatible to all of these different technologies. So even though, I mean, when you go out and a customer buys a modem, for example, and you look at the information, it has to be backwards compatible to all of these different technologies. So I wanted to make sure I covered just a little bit of that, where we've been in the past. All right, so let's go ahead and look at the future of FDX if we do move forward. All right, so we talked about this earlier, right? So what happens from an ingress perspective, right? If we deal with noise, we deal with other anomalies on the upstream, right? Now that the system is going all the way up to 204 megahertz, where's the FM band come in, right? In dealing with that. Well, now that we're going to expand in the future to upstream and downstream, where the upstream can be where, 600 megahertz, for example, the LT band at 750. Well, there's other LT band at 600 megahertz as well, right? All of this energy now becomes visible to deal with on upstream. So let's deal with the first example, which is the FM band, right? So depending on the bandwidth you're dealing, as we continue to expand the upstream, FM ingress, what used to be a downstream issue for customers, it was a drop-related issue, a network-related issue, for example. Now, all of a sudden, the systems are going to high split. FM is now a system-related issue, right? So you may or may not be paying attention to this issue, but once you start to go to the high split, it affects all of them. So because of the bandwidth of the OFDM band and the effects on OFDM carriers and single QAM carriers. Again, single QAM carriers are only going to go up to 85 megahertz, right? From that point, after that will be OFDMA on the upstream itself. So this is just the artifacts on it, and this is an example of this, right? So when the upstream is utilized for 4 upstream carriers, and now we, remove the entire portion all the way up to 204 megahertz, and then we just start to deploy OFDMA carriers, you can start to see 2 OFDMA carriers in the impact with FM ingress. All right, so this changes the paradigm of dealing with CLI too, right? So now you're going to deal with OUDP, all right, Oriental Frequency Division Multi-Axis, also known as Upstream Data Profile. Upstream Data Profile, OUDP, which is kind of a unique name, right? So if we're going to go ahead and expand the network to 204, right, and we have the aeronautical band, for example, the modems are now going to be within the OFDMA carrier. They're going to be tagged at 138 megahertz with OUDP technology in order for us to detect CLI on the upstream, right? What used to be a tagger on the downstream, now all of a sudden the modems will be deployed, or the modems will be given the capability for DOCSIS 3.1 to deploy OUDP on the upstream itself, right? So that's a different paradigm from dealing from ingress. I mean, to us, ingress and egress, whether it be upstream or downstream, it's similar in concept, right? But from a CLI perspective, now it becomes an upstream capability of verifying CLI with the cable modems being tagged with the OUDP technology. So again, it's just another example of how technology is going to change as we continue to deploy higher bandwidths on the upstream.
Juan, if I may, I have a comment on the FM piece of that.
Yes, sir.
So when it comes to FM ingress, things get really interesting when the FM band comes into the upstream, because let's just say you have a local FM broadcast at 100 megahertz, right? And you get one place where that's getting in. Well, of course, you could track that down and fix it pretty expeditiously. However, if on that same distribution leg you have 4 or 5 places it's getting in, it causes power addition. So you may fix one and say, well, it did make a difference. Well, it probably did make a difference, but because it's there in other places, it might go down just a little bit because of power addition, but you'll still see that carrier. So it'll be another peel the onion exercise where, okay, well, I fixed one, but that's just one. There's going to be more. So you may be going through that distribution leg a few times before you get all the sources of that FM ingress.
Absolutely. Absolutely. Yeah, well, you guys have probably heard of the term unity gain upstream, right? But think about noise unity gain, noise coming from subscribers and all those type of things. Well, the same concept that Woody just brought up, when you have multiple FM ingress, for example, right? And then the compounding that, it's going to hit back to, on the upstream again, depending on the bandwidth of your network. But yes, right now, FM for most systems is a downstream related issue. But as we move forward, it will become an upstream related issue. So yeah, compounding noise. Here we go. Okay, let's look at single QAM carriers and just characterize a little bit about those. Right. So when we look at level MER, BER, these are some of the things that we look at today within the carrier itself: echo, group delay, ICFR, hum. Right. So modulation techniques. The modulation contains the critical information on how to decode the single QAM carrier itself. Right. So in the network directions with linear distortions affect variations of this. It can affect the amplitude. It can affect the it can affect MER. It can affect pre and post bit error depending on how bad the roll off the suck out. The linear distortion affecting the downstream itself. So yes, these are things that we look at on a single QAM carrier itself. So some of the more enhanced testing, such as echo, group delay, any variations, any adjacent channel power that can impact the upper or lower channel, for example, right? So, which is completely different than that of an OFDM downstream carrier itself. So these are things that we've done for a long time. And some of the other things such as group delay and ICFR have been added because of voice over IP. So we want to verify what is the in-channel frequency response affecting the downstream carrier in this particular example, and what is the latency, and what is if you were to look at an equalizer, what is the echo due to the ICFR affecting the echo itself, right? And therefore producing the larger the index number, the better the lower the group delay, the better the performance. The lower the index number, the ICFR, the better the performance of a single QAM carrier itself, right? So over the years, we went from analog, which is visual representation of what happens when the level gets really low, right? And when you look at a digital carrier over time in the constellation, what happens as the level drops, right? The MER starts to drop, the constellation starts to expand. Well, as from an OFDM carrier downstream, for example, as the level starts to drop, the individual subcarriers, the MER will start to drop that as well, and therefore the constellation on a per subcarrier will start to drop, and therefore the low MER will. So everything that we've learned from an analog world to a digital world to an OFDM downstream carrier are very similar in concept. It's just the modulation is much different, and the correction for these technologies is completely different in order to correct for these types of problems that have been adopted over the years. All right. So,
if I may, Juan,
yeah, go ahead.
I think that's a perfect segue into my next poll question. I apologize to everybody. I didn't really know how these poll questions work, and I think it blocks Juan's screen when he's talking. So I'm gonna launch it right now, and let's just give everybody a minute to answer the question.
Oh, okay.
I think you're going to give the answer here in a second, and that's why I was anxious to put it out there.
Okay.
So I put it out there. So the question is, if I can read it because part of it's blocked. One of the features of DOCSIS 3.1 is to be able to adapt to degraded performance. To do this, the modem/gateway might. So please select one of the three answers: A, B, or C. A being request more input level. B, adjust the return transmit power. C, use a lower order modulation profile. So hopefully, let's see, we've got 28% voted so far. And looks like the majority are getting the right answer, at least I think is the right answer. I put these questions together late last night, so hopefully hopefully I have the right answer in here. Okay, give it a little bit more, give it another few seconds. Got 53% voted. But it seemed to slow down. 56, 58. Give it just a little bit longer. Got 60%. We're up 65%. So it looks like C is running way ahead of the others. Oh, we got 74% voted so far. So looks like we're going to hit 80+%. So it looks like it's stopped at 77%. I'm going to close it. So it looked like 79% pick C, which is use a lower modulation profile. That's exactly right. And I think Juan is going to go right into that. So thank you, everybody, for taking time to answer that.
All right. So again, let's look at a single quantum carrier as an example, right? So these are error corrections, right? And a single quantum carrier for error correction is a mean to deal with PDR. So I don't know if I'm getting an echo. I don't know if is that you, Woody, or anyways. Okay.
My mic, I forgot.
Oh, okay, no problem. Okay. Anyways, for DOCSIS 3.0.4 correction algorithm is known as Reed-Solomon, right? And this is a technology utilized in conjunction with Trails coding modulation, which is basically the ability. So one was giving us a much better dynamic range to gain a 2 dB dynamic range with error correction, right? So again, compared to the encoding that we do today with low density parity check, which is another technique that we're going to talk about in the OFDM carrier. This was done, primarily for single quantum carriers when it was introduced. Over time, it has dramatically changed, which includes the equalizer. Went from, I believe it's 14 taps to 24 taps and those type of things to add for linear distortions and the ability to make sure that it wasn't impacted to the input of the set-top box itself. So again, just another example of dealing with forward error correction. So if you look at this forward error correction, right? So a deep interleaf for digital videos, interleaf is often increased to provide better burst noise immunity. For DOCSIS carriers, better forward error correction, low density parity is also being implemented as well. So when we talk about the deep interleaf example, some of you might have seen it. So when we look at our spectrum, we may or may not know, what's a 256 and what's a 64. This is an old slide here because 256 quantum carriers were much higher in amplitude than 64 quantum carriers. 64 quantum carriers much more robust, and 256 needed a higher level in order to produce a better MER and therefore dealing with networks out in the field for the longer cascades, for example, right? So deep interleaf is a way of doing it. So it's part of the forward error correction. So if you look at this example, this channel, right, and you see there's a little tiny number right up here. It's known as the interleaf setting. So this is just 816. It's not even part of this table example right up here, but it is visible as different technologies became available. So over time, 1217 is another example. Now this is a 256. It's a 256 quantum carrier as well. And this is again 1217. This is 32x4. Now, if you were to look at all your DOCSIS carriers have an interleaf setting of 32x4, meaning that they can withstand a burst protection of 24 microseconds and 60 microseconds. So if 64 quantum, 256 quantum, right, in latency for both type of carriers, right, based on this technology, has a latency of 0.98 and 0.68 for 256. So this is the latency introduced by this type of technology, right? And basically, interleave effectively breaks up the information into different packet sizes and spreads them over time. It uses conventional interleaving, which specifies I and J, which is the number of taps being incremented between taps themselves, right? So think about the equalizers that we use in order to deal with a carrier, both upstream and downstream capabilities. So this is an example of just 32. All DOCSIS carriers, most systems in North America were using 32/4. They could use higher, but what happens when we ended up using voice over IP, they retain it at this. And the reason is, if you were to go from 32 to 128/1, for example, this is a digital video carrier, then latency, it has higher impacts at that point. So they decided to maintain 32/4 for DOCSIS and voice over IP traffic. So today, I think that probably 90% of all systems are using 32/4. They can use higher for deep interleave if required, right? So again, this is just an example of 128/4. Here's 128/4. For example, again, this is generally introduced more into video services, and certainly can. I've never seen a system that uses 128/5. I think we're kind of maxed out basically at 128/4, but you could see that you could certainly go higher, but therefore you can see the difference in burst protection, right? And you can see the latency introduced by that. So this is an old article from, I got this information from actually John Downey at Cisco at one point in my career, and I've used it ever since just to bring that information in. Okay, so let's go ahead and since we talked about, let's talk about some linear distortions real quick here, right? So throughout the network, we've got an optical node, all the various active devices, all of the various passive devices, and drop related issues, both any cut, any break, any change in impedance produces micro reflections, right? And this is really what has helped P&M group together the number of modems that are having linear distortions from an upstream perspective. Any modems that are going through that particular group, they're being grouped together based on distance, time, etc., because of the micro reflections, right? So this is, this is what's going on with P&M. But just talk about linear, non-linear distortions, right? So the basic review for this is just talking about two analog carriers, mixing the two analog carriers, mixing the two carriers themselves, producing what we call composite triple beat. Now, some systems were standard HRC, so the beat product generally ends up directly underneath the carrier itself. Composite second order, since we had an audio carrier itself, mixes the audio with the video, producing a composite second order, therefore producing what we call composite second order at this point, all right? So now that we've added digital carriers and you're mixing between the two technologies, I do have some systems that mix the two technologies together, for example. Therefore, in this mixing the two types of both analog and digital, then the beat product will literally run on a composite triple beat would end up on there. The mixing of the mixing of a broadband 6 megahertz continuous digital continuous type of carrier, for example, adds noise. Therefore, the noise would add directly underneath them as well as the composite in the second order, right? So you can see by mixing these, just by mixing the carriers, combining them, it's a production. So when you overdrive an active device, if you don't maintain unity gain on the downstream or upstream, it enhances these anomalies from one point to another, right? So now that we're adding an OFDM carrier, think about composite triple. Most systems have gotten away from analog already, or still retain some analog carriers for their AGCs. But think about the anomalies being produced, right? And today's meters allow you to visually see the spectrum directly, known as a vector, by using the constellation and producing a vector to look at the ingress directly at it. Years ago, when you were mixing these two technologies between analog, you were able to see the composite triple beat on digital carriers. Now that it's an all digital in combination with OFDM carrier, it's basically become a noise floor effect directly, unless you have other ingress. This has really nothing to do with ingress at this point. This is strictly just power of combining the carriers mixing the channels together and making sure that we don't overdrive the active devices when we're doing unity gain upstream and downstream, to make sure that every active device is set accordingly. The other issue that we deal with is common path. Common path is an issue, right? Because of the coaxial cable or passive devices, the difference between the center conductor being copper and in the outer sheet being aluminum, and the corrosion, due to some anomaly, just cracked cable or anything that produces that, and the amount of power and tilt at that particular location, and the mixing of every 6 megahertz channel produces what we call common path. This technology this anomaly is generally visually seen on the upstream, but now that it's all digital, you start to see humps as opposed to the 6 megahertz carrier that we've seen from the traditional video carrier itself. So that, has changed. Now that the OFDM carrier is being implemented, what does common path look like, as an example? All right. Now that it's a much more broadband type of carrier, all right, we still have it in today's networks. The other one is cross modulation. What is cross mod? If you've ever gone to somebody's house and they're still using, for example, dial-up, and they're making a phone call, for example, when they make a phone call, maybe you might have heard somebody else's voice, and you're hearing two voices, yourself plus someone else's. In the telco world, we call that cross modulation, or cross talk, for example. In RF world, we call this cross modulation. So if you have this carrier that goes up in level for whatever reason, the head end loses control of this carrier, what happens is the energy of this carrier is literally seen by this. So if you were to watch a TV program in an old analog, you would see the program of this channel, and you would see the program of this channel implemented on this carrier. So you would see a ghosting of this program on the backside of this particular program itself. And that's what we call cross modulation. In an all digital network, if this carrier goes up for whatever reason, the energy applies to this itself, but instead of seeing the video contents, as this particular carrier has multiple programs, what we see is a lower MER being introduced into the upper carrier. And that's right, if you look at your meter, it generally looks for adjacent channel greater than 3 dB to making sure that every carrier does not exceed a specific threshold in order to make sure it doesn't produce energy into the adjacent carrier itself. So these are anomalies, right, that has happened. So again, if this carrier was to go up and you double the frequency, you would create a harmonic. If this carrier was to go up, if you double the frequency, it would be a harmonic as well. You don't double the frequency of that. So these are what we call nonlinear distortions. And there's a great article by Ron Rannick, part 1 and part 2 on this example, right? So this is what we call nonlinear distortions, and common path is also this. So when we deal with these types of problems, we deal with combining issues, head-end related issues, active devices overdriving or something. That's when we look at these types of issues, right? The other problem is called linear distortions. So when we look at these individual carriers, each individual carrier has different types of tilts, right? Some more than others. Therefore, each channel has what they call micro reflections, amplitude, ripple, tilt, and group delay within the carrier itself, right? And these linear distortions are generally produced by, and 99% of the time or 90% of the time, are produced by passive devices, connectors, taps, et cetera, right? Could it be used by an amplifier? It could possibly use the housing, the setting of the housing, these type of things. Generally, some type of passive device is producing these anomalies, all right? Now that we're moving from a single QAM carrier to an OFDM carrier, you can see the response of the network, just like you see it here. You can start to see that as well, right? So when you have anomalies, linear distortions affecting the OFDM carrier, you're affecting a group of subcarriers within that carrier, just like you're affecting a suck out right up here on a single QAM carrier itself, right? So when we look at a single QAM carrier, right? So depending on the carrier you're looking at the level, the MER, depending on the artifacts affecting the carrier, you can have a linear distortion affecting the beginning of the frequency, the upper part of the frequency, the center of the frequency. When it comes to a single QAM carrier, the most important aspect of it is the single part of it, because if the impact to that due to a linear distortion, this has nothing to do with ingress, even though ingress may be another attribute due to the cracked piece of cable, right? But in this case, let's just say it's due to linear distortions. Therefore, it's difficult to demodulate that particular carrier. Now that we're moving on to OFDM carriers, if you look at your OFDM carrier, generally the meter will tell you where the PLC is located on these OFDM carriers, because we have to be able to look at that as part of the hierarchy to make sure that we capture the PLC, the filing channel, in order to we start the process of demodulating the carrier. So think about a modem has to scan, detect all of the single QAM carriers, has to scan and detect the PLC in order to capture the demodulate the process in order to get the rest of the content, such as the next code word pointer, et cetera, the A profile, right? So when you have linear distortions affecting the carrier, you can impact the carrier so dramatically. Therefore, just like a single QAM carrier, if the PLC is impacted so wide in amplitude, they can literally drop out the entire 96 megahertz carrier. All right. So these are just examples of linear distortions when we have to do. So when we deal with linear distortions, we break the problem into broadband problems, right? No matter what your cascade, the more passives and actives you have, the more possible that you're going to have a combination of multiple problems. The other example, broadband problem, it could be a standing wave, a low, slow rolling type of effect. A narrow band, it could be like a faceplate knocking out a group of channels, for example, and therefore difficult to demodulate a particular carrier within that group of channels. And then you could have a single carrier related issue, maybe like a radio crack, depending on the type of coax cable, underground, aerial, temperature, and all these other things, anomalies that can impact a particular channel or frequency. Now, again, these are different examples of that. All right. So again, I just wanted to cover a little bit before we continue to move forward with the rest of the OFDM carrier. I just wanted to cover linear and nonlinear distortions as part of that. So let's talk about the remote PHY capability, right? So we started. So why did we move to this technology? Again, OFDM, ortho frequency division multiplexing, right? The ability to deliver multiple, instead of delivering a single carrier, multiple subcarriers with different types of modulation. It's a basic analogy for this. All right. Why? Another reason is because a single QAM carrier can only withstand X amount of ingress and which amount impulse noise. So based on this information, you can have, for example, you can only withstand basically down to 1 microsecond. By having multiple subcarriers, longer symbol, you can do between 20 and 40 microseconds of burst itself. And therefore, an OFDM carrier can withstand more punishment on the upstream itself, on the downstream itself, since that's what we're talking about at this point. Each subcarrier can be there for 25 or 50 kilohertz spacing. Obviously, we talked about the bandwidth itself, right? So this is the reason why this technology, again, the expansion of bandwidth, right? OFDMA on the upstream, OFDM on the downstream, and the capabilities to deploy that. So let's look at the matrix that we're going to talk about. So let's go through some of this of the OFDM carrier as we go forward through in the capabilities and the recommendations per each individual. Notice that from a hierarchy, right, the PLC is the most important, the next code word pointer, the profile A, and then the average power, and then all the rest of the profiles, right? A lot of questions come up, is that, well, why not concentrate on power level? Well, power level is important. MER levels, the proper deltas are requirements, right? But you're going to find out that if the levels are really low, these guys down here, the PLC and this next code word pointer, can withstand a lot more punishment than some of these other profiles itself. So ultimately, yes, power is a recommendation, but ultimately we need these in order to get the rest of the information within the OFDM carrier itself. All right. So let's look at the methodology. Again, the carrier itself is broken down in either 25 or 50 kilohertz spacings, right? So think about 192 megahertz wide and replacing a single QAM carrier itself. That's 32 single QAM carriers that are going to be replaced. So think about a QAM carrier here, a QAM carrier here, right? So we did not transmit any data in the guard band. So this is one channel, the next digital carrier. Think about the guard band, right? Now, you're going to be deploying data in areas where we didn't deploy any data before. Obviously, we're not deploying any data on the lower portion of the OFDM carrier, but now we're utilizing the network much more efficient by simply deploying data in areas where we've never deployed, such as the guard band itself. So 192 megahertz will deploy a 32 single QAM carrier network, downstream. the number of subcarrier, a number of single QAM carriers themselves. All right. So generally, the recommendation is about 1 meg on each side of the OFDM carrier for the downstream. Again, bits per herd, right? And how many in really the modulation technique that can be delivered between a single QAM carrier and an OFDM carrier, and the abilities to therefore much more efficient, greater percentage, much more, I mean, 35% more efficient than that of a single QAM carrier. That's a big deal, and that's the reason why we've gone to this technology, right? So let's look at a single QAM OFDM carrier, right? And let's, for low frequency, upper frequency, let's go ahead and move this. I like using this analogy just to break the OFDM carrier down. So think about each individual subcarrier, right? Each individual subcarrier delivering delivering data. So let's look at it from this perspective. When we look at it from this perspective, we're going to look at it from the profiles. We're going to look at it from a few different ways on how the carrier is actually implemented and how the modulations are going to be effective for this OFDM downstream carrier. All right. So let's look at a single QAM carrier. When data is delivered on a single QAM carrier, it's what we call a serial, right? So the next bit comes in, the next data comes in according to either 64 to 56. So this is a common technique, whether it be 6 megahertz or 8 megahertz, which was used in European, in EMEA, for example, right? In North America, we've all used 6 megahertz. But this is a common way of delivering data services, and we still do that today for both DOCSIS, single QAM carrier, and for digital video carriers themselves. All right. So again, when we look at single QAM carriers themselves, right? Think about single QAM carriers and the ability to handle FM ingress, OFDM carrier with very little ingress, right? Optimize the network in order to have maximum profile capability, and then OFDMA carrier on the upstream, which we'll talk about later on, and how segregate that from single QAM carriers themselves as well. So just 3 different views: upstream and downstream capability. Right. In this case, when we look at the OFDM carrier, right? So each carrier itself is being delivered, right? This is the way that we deliver. So all of the subcarriers have different modulation, delivering each bit of data across the OFDM carrier, right? So this is a way of delivering this much more for. Think about it, when you combine 32 single QAM carriers, right? You have to be able to deliver all the data. You got to have all the and then combine all the data at the other end. So in this case, this is one way of actually combining the data from a parallel perspective and deliver one large massive amount of data to a receiver on the other end, right? As opposed to single carrier, a serial, much more easier to deliver the content parallel. They're with various different types of modulation. Again, remember, the spacing of the carriers could be 25 or 50 kilohertz. Obviously, the demodulation processes and FFT or fast furious transfer as well. All right. So these are multiple subcarrier slots within the carrier itself. So when you look at your meter from a data perspective, code words start at the lower part of the frequency and then they populate upward. Next code word pointers start at the upper part of the frequency and start to populate downward. So they start to populate downward while the code words start to populate upward in frequency itself. So again, remember the frequency, the lower frequency is up here, the upper frequency is up here, right? We've got them agitated. So we can see here the max modulation for the type of profile that we're using based on this, as opposed to a single QAM carrier that's basically using serial data parallel, right? Again, just a breakdown of the OFDM carrier. So OFDM modulation, right? It doesn't just modulate all the carriers at one time. What it does, it actually shifts, right? As it goes on and on in order to do that, right? So as one carrier is modulated with data, the next carrier is not doing it, and they're all staggered off center frequency in order to make sure they don't produce any anomalies internally within the modulation. You can have problems within the OFDM carrier as well, all right? But this is actually, because of FFT and ortho frequency, this is really how it's actually managing the data and the subcarriers as it delivers the information, all right? There's gonna be a little bit more breakdown the way we talk about this.
And
So,
go back to
oh,
that
go ahead.
real quick, Juan, and just like to point
Yes, sir.
out one thing. If you look at the green subcarrier, and then I think to the left you have an orange and then a blue,
Yeah.
and you see those overlap. So your initial thought is, well, that has to interfere. The green has to interfere with the other two, or vice versa. But hence the term orthogonal, meaning that when the green peaks, the orange subcarrier and the blue subcarrier are at a null point, or zero. So that's how you prevent them from interfering, because there's actually a time element also.
Absolutely. Absolutely.
So
And there is intercarrier interference. It has to be verified, but those type of things. But man, it is amazing to see the speed in which this modulation occurs.
yeah, it is quite amazing, and the spectral density is just so much more dense than SE-QUAM. And like you said, 30%. You're increasing your spectrum efficiency by 30%, OFDM versus SE-QUAM.
All right. So another possibility within OFDM carrier is called exclusions, right? And exclusions is simply the ability to tell the OFDM carrier within a particular part, either due to issues or profiles, not to transmit any data within that carrier. And this exclusion is done for several things. Maybe part of the profile, or it may be part of the modulation, because you need that portion of the bandwidth in order to add a single QAM carrier itself. So they can actually wrap an OFDM carrier around a single QAM carrier itself. And it can be a DOCSIS carrier, and it can be used for data bonding as well. Or it can be a digital video carrier itself, but it literally allows you to really wrap around the carrier itself. So exclusion zones are not uncommon to see that, right? And the exclusion zones can vary in bandwidth. So again, that example, again, exclusion zones, we use exclusion zones on the upstream in order to set-top boxes. Some systems deploy the 5 to 42 and OFDMA carrier. So we use exclusions on the downstream as well as the upstream as well. I mean, just showing you an example of how systems use exclusion zones, because sometimes they deploy the carrier and they may or may not be able to move a single QAM carrier for whatever reason, older set-top boxes, et cetera, et cetera. So this allows for this capability. Single QAM carriers, we just put them where we want them, and we tell the modem what carriers are going to be used in order to bond together. But in this case, it allows you to separate the OFDM carrier. All right. Okay, so the next one is data or code word errors, right? So how do we verify correctable and uncorrectable code word errors? So at the very top, this is an example of the next code word pointer, and this is our code word. Code word B, profile delta, code word A, profile Charlie, right? So think about all of the individual subcarriers, different modulation, right? So all of these right here is one symbol. So all of these, which combination of both the next code word profiles, the B profile the delta profile and the Charlie profile are part of the same symbol, right? So you could actually break it down and deliver it as the data is being delivered itself. Right? So one modem can be receiving, or multiple modems can receive, or the same modem can be receiving all of this different information on different profiles. All right. It could be a larger profile depending on the type of modulation. Since the CMTS and the set-top box, or excuse me, the modem are constantly communicating, they determine what is the highest possible profile to utilize to deliver the maximum content at one point, instead of derating the different subcarriers, in which they can, and that's the reason why we have different profiles to deal with this capability, right? So again, this is just an example of each symbol delivering different data, possibly to multiple modems, single modem, etc. All right. So that's just an example of that. Remember this, and this is important later on, because when we deal with noise and ingress, code words start at the lower part of the frequency, and next code word pointers start at the higher frequency as they populate downward, right? From that perspective. So think about this information and code words populate downward. So when you have excessive noise and ingress on the lower portion, what does it affect? When you have excessive noise, linear distortions, whatever, on the upper portion of the bandwidth, what does it affect the carrier itself? All right. I say this is an example of error correction in the term low density parity check, right? In you know, it's pretty incredible. Just like we talked about the single quant carrier, the capability of increasing the dynamics of correcting code word errors, like pre and post code word correction you've been dealing with on the upstream from 3 to 6 dB of gain. That's a big deal, especially if the OFDM carrier is being deployed somewhere between 5 and 10 megahertz, for example, right? There, you know, obviously the profiles are going to be different for that type of profile as opposed to a carrier that's at 96 megahertz on the upstream, an OFDMA carrier on the upstream, for example. But for downstream OFDM carriers, low density parity check has really, you know, increased the dynamics to deal with linear or noise, and et cetera, to maximize the capability of that OFDM downstream carrier. So I think was there something you wanted to say about this, Woody?
No, but if you want to pause, I can launch the final
okay.
question in our poll.
Sure.
So I'm
sure.
going to try launching it now. So the question is, OFDMA is typically used in the A, upstream transmission, B, downstream transmission, or C, both. So we'll give it a second. 34% voted. %, so we'll hang on there for a second. We're up to 66%, so give it a little bit longer here, 71%. So we're about to hit 80% here in just a second. Got a couple more people to vote, and we'll be there. Looks like the voting slowed down quite a bit, so I'm going to go ahead and close the poll in just a second. So 59% voted upstream transmission, 10% downstream transmission, and 31% both. The correct answer is actually upstream transmission. So we only use OFDMA in the upstream. So thank you guys for taking time to use the poll, and we'll go ahead and let Juan continue. Yeah, Juan, I know for this error correction, I didn't have anything to say other than, you know, low density parity check is just a game changer when it comes to
this. Yeah, absolutely. The technology is. I think Woody might be busy, so let me move forward. Okay. All right. So let me move forward with profiles, right? Profiles are going to help us deliver variations of speeds based on the requirements. So this is just a basic example, right? For an OFDM, you got A profile, B profile, Charlie profile. You can have up to 16 profiles, right? Most systems deployed about 5 profiles, between 4 and 5 profiles. Some systems did less. So this is an example, right? If you were to look at the kind of the motorcycle up here, right, and the train example, right, different types of modulation. This is just not, this is again a basic example. Really, when you look at it, it tells you right here. So the meter's telling you what is the max modulation for the different profiles that you're running. Again, this is an example of a system just running A and B profile. Most systems run at least 4 or 5 profiles in most cases. Right, so again, this is really what it is. A profile can be a combination of mixed mode, which includes exclusion zones, right, to deal with issues, right? Charlie profile, etc. So this is again just a variation of profiles with mixed modulation to deal with system-related issues that are required. So they could even do testing. They can do a test profile modulation and see how modems do, and then they can deploy a profile. So systems can actually manipulate profiles to their needs. You know, systems that have longer cascades as opposed to systems that have shorter cascades. So all of these are variations to working with profiles again. So think about this, right? You have an optical node, you have the distribution, Some systems, again, the average system has about 6 or 7 amplifiers to cascade, you know, and maybe the line extenders 8, et cetera. But most systems are moving down, and you know, some systems only have a node and 2 active devices, less than 125 ohms per customers per optical node. So they vary. Those are all variations. But in reality, the ability is that OFDM and single quantum carriers, you have to make sure that the system can support max modulation. So wherever you are, however many active devices you have, you know, with the exclusion of issues, excluding issues, you should be able to support all the max modulations, all right? But when the issues do occur, that's when it's really nice to, you know, you're gonna have customers with various different services, so therefore different profiles can be delivered for those subscribers with various different services, right? And that's just an example of it. So.
Yeah, I do have a comment on this, if I may, Juan.
Yeah, sure.
You know, one thing we were talking about on the DOCSIS 4.0 readiness committee was looking at those profiles and looking at information coming from the modems to be able to assess whether, you know, at what speeds that customer could subscribe to without doing anything, right? In some cases, maybe they get, you know, they could qualify for the highest tier of throughput, and maybe not, because maybe there's issues, but we could also use that information to kind of estimate, saying, hey, you might not be able to get a, you know, full 6 gig down. Maybe you know, you go to a 2 gig downstream would be your maximum. And that could also determine whether we have to send, you know, a qualified installer out there to work the, you know, inside part of it, or if there's a plant issue. So there's a lot of valuable information in those profiles that we can use to determine what the customer qualifies for as far as throughput.
Yeah, PNM has certainly given us a lot of information from the cable modem box to figure out what's going on at the input and output. I mean, yeah. Okay, so let's look at the first example, the PLC, right? Part of that, right? So again, when we look at the PLC, is where the information is located as far as the filing channel, right? So in this case, we see that information. You can see the pilot carriers and where generally have. Now again, this is an example of the PLC and how it's broken down. So let me, this is an example. Again, this is just an example. I was able to break it down, looking at all of the carriers. So again, the PLC has a region, and it's allocated with pilot carriers on each side to make sure that the modem can scan and detect itself. So again, the OFDM carrier can be broken down in various different ways, and everything is actually allocated. Every pilot subcarrier is assigned a particular either modulation or pilot carrier, et cetera, or exclusion zones. All of this, again, this is just a general example of it, but in reality, it can be mixed modulations and variations. So again, this is just an example of breaking down the actual, you know, OFDM downstream carrier. But in this case, again, we're concentrating on the PLC, right? And the PLC is where we look at the filing channel. Again, it's generally 500 kilohertz, so often most subcarriers. And again, the type of modulation is generally QPSK. We have to make sure that we detect this carrier, all right, in order to just. So if we look at this, when we look at profiles, the number one thing generally at the top of the meter is generally the A profile. We want to make sure we're locked. We have correctable and uncorrectable code words. We could have some correctable code words. A lot of systems deploy this as a 64, and then they've gone to 256, and they have some errors showing slightly in this case. And then as long as we don't have any uncorrectable code word errors, right? So you got to figure out what's going on. You should be able to track this back to the node, et cetera, to figure out if you have correctable code word errors that are happening. The main thing is we have to figure out if they're run to uncorrectable at that point. So again, the recommendation right here, I mean, this is a low MER, right? Generally, the MER is very high because of the type of modulation that we use for this type of carrier itself. So the levels can get down to a -15. So think about the drop, the recommendations for a single QAM carrier plus or minus 10, for example, right? In this case, they can recommend a -15. The problem is if you get down to a -15 to deliver the PLC, but what happens to the other subcarriers who have 4K modulation, all right? So those are the things that you have to be concerned with. So yes, it's very robust. It can certainly handle that capability for dealing with. So in this case, you can see that the A profile is modulated with 256 QAM, all right? Some systems do it with 64 QAM, QPSK, the variations of the A profile.
One thing,
Okay, let's go. Yeah, go ahead.
one thing that's changed between SC-QAM and OFDM. If you noticed, with your meter previously with SC-QAM, if you had prefect errors, you would be concerned, right? You'd be chasing.
Right.
But
Exactly.
with OFDM, there is prefect error, so you shouldn't really overly worry about those prefect errors, because there will be some. It's not perfect, so there'll be some errors, but you just focus on the correctable errors, because that should always be 0. Now, if that comes up not 0, then you got some work to do.
Yeah. It is not uncommon. I go to some systems to see some errors on the A profile here. And usually that's what we're looking for, is uncorrectable code word errors. Again, unless the index number, the exponent number becomes very, very small, then they can certainly impact the carrier. So the next example is the next code word pointer. Remember code words start at the lower portion of the month and they populate upward, right? And the next code word pointer start at the top of the carrier frequency and then they populate downward, for example, right? So when we look at the next code word pointer, the mode in which code words are present on which profile to find each code word. Code words are analyzed, it's critical for the proper data. So again, in this case, we look at the next code word pointer, right? We look at the PLC, we look at the next code, we're sure we're locked, and generally we look at this profile, right? Excuse me, the modulation, right? Generally, I mean, 16 QAM is a very robust carrier. Not to withstand anything that most systems can produce. I mean, unless that's why they were accepting like a -15, right? That's too low for some of the other things that we're going to require. So again, an example of that itself. So again, this is just a variation, right? So in this case, this guy is gone, the A profile is gone, all the carrier is gone. Even though the carriers are there, we're not picking up anything else, right? So we need the PLC. This is just aggressive suck out. I'm just sucking on the carrier because I want to show that the PLC is gone. Everything else is gone, right? Even though the data is there and the carriers are. But since we cannot get the PLC, we can't get the next code word pointer, the A profile, we're not able to get the rest of the information because it's simply gone at that point, right? Again, it's just a visual representation of the effects on an OFDM carrier, right? Let's go ahead and go to the profile. Excuse me, I think that was. Okay, let's go look at the levels themselves, right? So when we look at the levels, right, we give such a large carrier. Right? We got the average, we got the max, and then we got the minimum. Remember, it's a 96 megahertz wide, 192 megahertz wide, for example, and then we verify the in-channel frequency response. So the recommended level for this carrier is greater than a -6, right? So the average level is recommended in order to support these different types of modulation. So this table up here, at a -6, you can still support 4K modulation. So if you're at the drop in the customer's home and you get down to a -8, 9, 10, 11, 12 as an average power, then you can start to affect the delivery of higher modulation, right? So remember we need, subcarriers need better MER, right? So if you're already playing, that's why that other example at minus 15 for the PLC, et cetera, it's great for these guys, not a problem for these guys, but it's a problem for the higher modulation delivery. Again, just as an example of looking at the carrier itself, right? So when we look at levels, right, we look at the PLC dropping, you can see the average MER right up here. So when we look at a channel, we try to compare that to a single carrier itself. So when we look at this average level, is that that's equal to the other carriers themselves? Again, we're taking a large group, breaking it down into 6 megahertz chunks, and therefore comparing that to a single QAM carrier itself. All right. Again, the objective is not to get any lower than -6 average power. All right. What I'm going to do is that I don't want to run out of time, so I want to go ahead and concentrate a little bit on the OFDMA upstream carrier. Right. So let's go ahead and move on to that. All right, so what we're going to talk about an OFDMA carrier and some of the capabilities, one which is what we call mini slot sizes. It's called CMTF map of mini slots. Intervals uses code. So each upstream carrier or group of mini slots are giving what's called interval usage code, all right? There's different codes to be utilized. There's pilot patterns, circular prefix, and 96 roll-off period, and the MER per subcarrier, the in-channel frequency response. So these are some of the things that we're going to talk a little bit about then. So let's go. We already covered the OFDM carrier, all right? We cover the OFDM structure and the capabilities. So when we talk about an OFDM carrier bonding, for example, must support 8 single QAM carriers, all modems, right? The 3.1 modem must support 2 96 OFDMA carriers. 3.1 modem must support bonding between OFDMA and single QAM carriers on the upstream. So these are the basic capabilities of that, right? The ability to support a very large OFDMA carrier with single QAM carriers all the way up to 85 megahertz themselves. 3.1 will support 204 megahertz. So again, these are the types of subcarriers. Subcarriers can be defined just like we did, again, 50 kilohertz and 25 kilohertz and 50 kilohertz. Just like we did with the OFDM carrier, the same thing, right? So that's what, over time, some of the systems, and I forgot to mention this earlier, some of the systems have gone from 50 kilohertz spacing to 25 kilohertz spacing on the OFDM carrier. And I know we're talking about OFDMA right now, but some systems have already changed and therefore added more subcarriers, right? So if your spacing goes from 50 to 25, you can add more subcarriers and therefore modulation, right? So again, we call this 4K in this particular case for update. We call this 4K and 8K type modulation, and various modulations for that, right? Pilot carriers are primarily BPSK modulation. They have to be very, very robust in order to make sure that we lock into the OFDMA carrier due to all the ingress on the upstream. So upstream pilots are subcarriers that do not carry any data. Instead, the pilot subcarriers are encoded with predefined BPSK symbol known as the receiver. The pilot carriers are the CMT's receiver adapt to channel conditions and frequency offsets. So again, a basic example of that, right? So we take the data, we encode it binary, and then we add the VPSK itself. Take this in this example right there. There is a difference between, it shows the time difference between the right pattern corresponding with situation of the frequency domain. So in this case, we have the carrier, the encoded, and then the carrier with the modulation. And this is what we see on the pilot carrier itself. Again, pilot carriers have to be very good on the upstream. And we talk about the downstream, the pilot carriers for the downstream for the OFDM carrier, but certainly for the upstream because of all the linear distortions that we deal with, primarily noise issues that we deal with, right? So what is the difference between an OFDM and OFDMA carrier, right? So we talked about earlier how that data is being delivered across the same concept, right? A parallel example, all right? OFDMA delivers that in a parallel example. Each individual subcarrier varies modulations, right? But this is what changes a little bit with OFDM and OFDMA as an example, right? When we look at each symbol, each data row is a symbol, right? So the symbols are broken down into frames, and the frames can be 6 to 32 symbols, 6 to 32 symbols themselves. The subcarriers are grouped into mini slots, right? Therefore, each individual frame is broken down. Subcarriers can be bit loading. So here's a mini slot number 1. It could be 8 to 16 subcarriers and various modulations. And this is right there. If you look at your spectrum analyzer and you see how sometimes data is transmitted on the upstream, you see how they're grouped together, how the data is actually grouped together as it uses these frames and mini slots itself, right? Well, the OFDMA has also what they call exclusion zones. So the exclusion zones are also so what they do is they create a mini slot, and in between the mini slots, they add the exclusions that are required itself as well, right? Earlier, I was showing you on the upstream, just like the downstream exclusion zones. Well, this is a system that can be using that. A lot of systems decided to use exclusions specifically for their set-top boxes. Since the system is still mostly 5 to 42, they deploy the OFDMA carrier between 5 and 5.5 megahertz and 20 megahertz, and allow the set-top box to deploy by adding those exclusion zones as an example, right? So again, unused, right? Excluded frequencies occur between the mini slots. No carrier or data is allowed. Unused frequencies may be defined and occur between the mini slots themselves. Unused carriers are used for pilots transmitting probes or PNM. So in this area up here, they put pilots or probes for PNM in order to capture information to see what's going on with the carrier data information as well. So this is a way of actually breaking down the OFDMA upstream carrier itself. Okay. Now, we talked about profiles early on the OFDM carrier, right? Similar in concept, right? Profile A, B, C, Charlie, etc. But it's a little bit different when it comes to upstream, right? So now, profile Delta, Charlie, profile A, each profile specified, bit loading and pilot pattern for each mini slot. So therefore, one mini slot, well, that mini slot is an example, right? So therefore, in conjunction with the pilot carriers and certain the patterns and how they're broken down into smaller groups. We're still remember, so when the OFDM carrier transmit, it is still considered one symbol, the next symbol itself. But those group of symbols and in combination of pilots are creating our mini slots and profiles as well, right? So it's similar to the OFDM carrier, but it's a much more broken down, and we'll see how that looks like when we look at it itself. Let me look at it. Let me move forward because I don't want to run out of time here. Let me here's an example. I'm just using Patrick in an example, but watch how the mini slots work, right? So right now, it's a possibility, obviously a high possibility, that a modem is transmitting on all of these carriers themselves, and it's using this portion of the OFDMA carrier, right? This is the exclusion zone for the set-top box. So as the traffic is embedded, at this point, it's using all of the upstream traffic. In this case, the 3 single QAM carriers, 64 QAM, and all of the mini slots within that OFDMA carrier, right? So again, it's just an example of how traffic is being managed from an OFDMA perspective, okay? Again, this is just an example of managing the difference between the two. Before I conclude, Woody, is there anything else?
Yeah, well, when you're finished, I do have some shameless plugs.
Are you? Okay, okay. No problem.
So,
Actually, this is pretty much it. Go ahead. I'm
okay,
sorry.
so I just like to talk to the audience a minute about future events they're coming up. So for June, I believe on June 21st, we're going to have a seminar on outside plant powering. We're going to have Scott Johnston of Comcast and also George Bossack of Intersys do that presentation. Let's see, in July, we're going to have Rich Hager, yeah, a long time, a former colleague of mine when we were at TCI. So he's been around a while. Going to go over mid-split, high-split amplifier setup and balance. That's in July. In August, we're going to have PON networks. I'm working on a speaker in September for leakage and LTE. And then in October, we'll have tap equalization. In November, we're going to have a technology and training summit, and our focus is going to be on preventative network maintenance. And in December, we'll wrap up the year with TDR basics. So got a lot of good training coming your way. We'll get the announcements out to everybody, and hopefully everybody can get signed up, and we talk to you then. So is there any last questions? I don't see any in the questions box at the moment, but I'd just like to say thank you for everybody attending. Juan is a great presenter, and I learned a lot today, and I hope everybody did the same. And so thank you again, Juan, for doing this
No problem.
presentation.
My pleasure. Thank you for having me.
Okay, we'll end the session there. Everybody have a wonderful day. Thank you.
Take care, everyone.